Hello class, now we're going to look at chapter 18 on geologic time. So the picture that you see here is my sister in the Grand Canyon a few years back. If you have ever been to the Grand Canyon, or so many other canyons really in the West, it's very amazing to even think about the amount of time that is recorded by the rocks that lie on either side of the canyon on the walls. In the Grand Canyon, for example, the bottom rocks are of Precambrian origin, meaning they're older than about 500 million years, some of them even reaching ages of 2 billion years. So amazing how much time is encompassed within this canyon. Well, I'm going through this basically to tell you that rock strata are like pages in a book. Each stratum has some content about some of the events that occurred, and altogether, all the strata, they make up the record or the story of the area. And just like the pages in a book, especially of an older book, if you can think of that, the early pages of the book are a little bit damaged. Some of them are missing, some of them are torn, some of them are smudged, because usually people pick up a book and they stop reading it after a little bit. So the earlier pages tend to be more worn out. So again, same things are going to happen. The strata that are older and have been around for longer have also undergone more alteration and are sometimes broken up. They're altered greatly or they're missing altogether, as we'll see later on. But overall, the full strata provides clues towards the necessary information that shape and reconstruct the events that occurred at any one location, at any one geographical site. So what you see here is a set of pictures of Arches National Park. The top left one is of me a few years back. The other three are from a trip this spring that I took with my husband and one of our best friends. But here you see a massive rock strata as well, like you saw in the Grand Canyon, perhaps not as massive, but still pretty great. Along with also very amazing arches that were caused by processes acting on the rocks after the sedimentation. For example, processes such as uplift, erosion, the faulting, and other ones that have shaped this land to be what it is now and what people go there to look at. So in the next few slides, what I'm going to do is continue to show you pictures of me and my family and friends in all of the areas that display where we've been, and many of these areas contain the different types of rocks. So you're going to see mostly sedimentary rocks, as they are the most common ones at the surface, but you're also going to see some igneous rocks and some metamorphic rocks, along with the pictures of myself and my family again. So in this slide, you see my mom, who is in Death Valley on the left picture. So she's with tilted layers that have been tilted at Death Valley. Most of these are sedimentary layers, but you see just how cool the colors are. So you see the variation in environmental deposition most likely. And on the right side picture, you see me hiking up of one of Yosemite's hikes on the Sierra Nevada batholith. So this is all granitic, igneous intrusive rocks. So here are some of the sedimentary rocks in Canyonlands National Park and in Zion National Park, respectively, left first and then right. And by the way, both of these are expressions that we see, or on which we see the amount of erosion that has been imprinted on these rocks. Also, within them, we see the type of weathering that has taken place. For example, on the left picture, we see the spheroidal type of weathering within those rocks. So in this slide here, you see my sister jumping on top of the mud cracks that are currently forming and will be sedimentary structures at some point once they lithify, and they'll be able to tell us of today's environment in the future to come. You see Marshall, my husband, in Yellowstone Canyon on the right side picture. And you also see me and my research group taking samples on the hot springs of Yellowstone. This is way back in the backcountry. But in these areas, the soil was so acid, the pH of the fluids near there was about 1 to 2 of pH. So the soil itself was pretty acid. which is what caused our pants to tear, as you're seeing in the right top picture. Also, you see within this specific photo the amount of dead trees that are around the areas, and that is representative of the amount of CO2 that is being released at the site, and hence causing the amount of, I guess, dead vegetation. All right, so here you see environments that have been extensively glaciated, making the igneous rocks exposed and jagged on the right-hand side, and then the second, or the left-hand side, is exposed limestone or more calcareous type of rocks, and this is in Canada and Banff. The first one I should say, or the right-hand side one, is in the Sawtooths here in Idaho. So in this slide, you see the Sawtooths on the left-hand side and my dog Kala. Also, you see the batholith that has been glaciated there. That's the Idaho batholith. There's more limestones that have been glaciated on the left bottom picture. And on the right side, you see a set of basaltic rocks. On the top right, you see the Palouse Falls in Washington. And those are going to be Columbia River basalts floods that are kind of encompassed here. So you see one flood here, another flood right here, so on and so forth. And on the bottom, you see basalts that are located right here in the Snake River. This is just a little bit off Swan Falls, which we'll go to during our field trip. Okay, so here you see Kala, again, my dog, posing in front of an arch of rhyolitic rocks. This is in the Owyhees, so this is pretty cool. You should check it out since we're so close to it. You might as well. And then this is Marshall walking through a crevasse / kind of cave that has been developing in Canyonlands National Park. And that crevasse or cave is within this massive sandstone structure that is, I don't know, at least 30 or 40 meters above him. In this slide here, you see all the desert landscapes of southern Utah pretty much. So you see in Canyonlands National Park, all of these I should say, are in Canyonlands National Park. What I'm showing you here is the horizontal beds that have been greatly eroded on the top two images. You see on the bottom left a clear, distinct normal fault, and we'll cover normal faults in chapter 9. And then on the right bottom, you see the ripple marks of some sort of paleo flow. So in this case, the paleo flow used to be towards the kind of left and bottom of the picture. And we saw this on chapter 7, to how to determine the flow. The more gradual side is going to be where the current's coming from, and then the more steep side of the ripples is going to be the side where the flow is going towards. So finally, here you see another picture of my parents that are posing in front of more Columbia River basalt flows. You see columnar basalts in the bottom left, and this is in the island of Providence in Colombia. You see Marshall in Providence as well, with the coral reef that makes up the calcium carbonate structures. And then on the top right, you see a lot of philitic rocks. So those are the metamorphic rocks that have undergone low to medium type of metamorphism. This is in Madison Valley in Montana. So all in all, I have showed you all of these pictures because luckily I have been able to go to all of these amazing places. And upon going, I've been able to make inferences about past events based on the rocks that I've seen. And thanks to all these structures that they have had, or the different clues that I've seen based on their erosive patterns, and also based on the rocks that may overlie or underlie them, and the deformation that they've been subject to, all of these aspects ultimately is what have helped me and other geologists, many other much better geologists probably, put together a geologic framework, a geologic sequence of events that have helped us understand what is going on with the rocks throughout a rock record, a specific rock record. So interpreting the Earth's history is in fact one of geology's primary goals. And we do this thanks to all of the clues provided in the rock record itself. Thanks to this, along came the making of the geologic timescale, and you can think of it as a calendar kind of for geologic events and different rock units. So without this time scale, knowing single events without some sort of reference as to when they occurred would be like knowing about the Civil War, for example, but not knowing when it occurred. And hence, it could be taken out of historic context if, for example, you assume that it happened in the year 2000 as opposed to the 1860s. So the same thing happens with geologic events. If I know, or if I think that perhaps a meteorite occurred a million years after it really did, then I can be taking things out of context and not understand what's going on around the area where the meteorite is, for example. All right, so the geologic time scale, which is in the image on the slide, or I guess is the image on the slide, it's a pretty complex tool. It's made from data that has been gathered all around the world and will separate different events and rock units based on specific subdivisions that could be tracked throughout the world. So within this geologic time scale, we measure time in millions of years, which obviously to us seems daunting, but a million years is a tiny increment in historic time of our Earth. So through the geologic time scale, people have learned that the Earth is much older than we had previously imagined. And that the surface of the Earth and the interior have been changed over and over again by processes that are still ongoing today. So processes that we see today deforming rocks are the same processes that shaped the Earth before in the past. So ideally, if we were to look at a rock, we would be able to pick it up and basically give it a specific age following that geologic timescale. And sometimes we are able to do this through methods such as radioactive dating, which is a method that only came about the 1900s, and one that we will cover later in the chapter, or in the lecture, I should say. However, this is not always the case. We can't always go ahead and take a sample from a rock unit and take it to the lab and have it dated, partly because we don't have the tools, and partly because there are no radioactive isotopes within that sample, and so we can't do it. So we use other types of principles and tools in order to constrain the age of that specific rock unit. And those principles that we use are what make up relative dating, which are qualitative methods used to date a rock based on the qualitative characteristics of it rather than the quantitative ones. For example, let's take this set of twins right here. Obviously, these twins are nearly the same age, almost exactly the same age, but one of them is officially older than the other one, right? And we know this because one of them had to come out of his mother's womb before the other one. So saying that one came out before and hence is older than the other one is what we call relative dating. We are going to say that one is relatively older than the other. Maybe not, we don't know exactly how many minutes or seconds older, but we know that it's the older twin is older. However, if the specific moment where the twin came out of his mother's womb was recorded, and then the birth of the second twin was also recorded, and it was to be 4 minutes and let's say 23 seconds, then that would be a type of numerical dating. We have a specific quantitative measure of when they were both born, so we know how much older one is from the other. But if we didn't, it would be relative dating because we just know one is older than the other. So when we use relative dating, we're placing rocks in order of formation. So there is no age that is given to them specifically, but rather they are placed in a sequence of formation, which indicates which of them form first, which of them form second, third, etc. So these techniques used to relatively date events are still used today and are incredibly valuable and useful for preliminary research. So the methods that we will look at in the next few slides are the ones that were used to make a relative time scale at the beginning of geologic study. So that relative timescale was eventually supplemented by numerical dating, which provided the quantitative addition to this tool.